Just a minute. I've lost my, okay, from Berkeley, from UC Berkeley, but he's also at the Challenge Institute of Quantum Computation at Berkeley. He's an associate professor in mathematics. What's that? Yeah.
No, go ahead. Yeah.
And also a faculty scientist at Lawrence Berkeley National Labs. So although he's still relatively young, as you can see, he has already had quite a distinguished career. So he started with a BS in math from Peking University, and then went on to do a PhD at Princeton with a very well-known and distinguished mathematician, Weinan Yi, and also with Roberto Carr in chemistry. And now, usually I don't like to read out the awards and things of our visitors, but in this case I got to because, well, so he won not only an NSF Career Award and then the PCASE, the Presidential Early Career Award. He also got the DOE Early Career Award and the Siam Computational Science and Engineering Early Career Prize. So he's won pretty much all of those early career ones. And very unusually for a mathematician, right? He was just part of a team that won the ACM Gordon Bell Prize for high performance computing. So this is a very big prize in large scale computing on exascale computers. And I don't know, well, I guess Weinan was on that work too, right? So you must be among the first mathematicians to win such a prize, right? Did you do the coding yourself, Lin?
I'm going to talk a little bit about that.
Yeah, but were you running the simulations yourself?
No.
No, I didn't think so. So he works in a huge variety of areas, obviously numerical analysis, quantum many-body problems, quantum chemistry, material science, and so forth. And I also recently discovered that he has a very nice introductory book on the sort of mathematics behind electronic structure calculations, published by Siam, I think last year or the year before. Okay, so with that, take it away, Lin.
Okay, yeah, thank you very much, Kieran, for the very kind introduction and invitation. It's a great pleasure for me to give this talk in front of some, I can see, experts in this topic. And I'm going to talk about relatively recent work joined with Professor Lexi Ying, Stanford, UA his former postdoc, and also my former postdoc Leonardo Cepeda-Mendez, who is now assistant professor at UW Medicine. It's on the multiscale neural networks. If time allows, I'm also going to talk about how to learn electron density, which is kind of related to this topic. So our goal is to learn a nonlinear network using machine learning. It's pretty general. You can think that you have some input, I call it V, that's in some domain in Rn, and I want the output is some U, and it's in some other domain, which is in Rm, and you can query this kind of F again and again and again. In the end, you just want to learn, okay? So there are many examples, numerous things can be really formulated in this way. In particular, if you're solving the differential equation or the integral equation, V is somewhat your input, U is your solution, and you want to solve. Our favorite example is Kohn-Sham math, of course. And so this is a set of nonlinear differential equations. I'm simplifying things a bit to become a set of linear eigenvalue problem. So given the external potential V, effective in the sense that I'm talking about the non-self-consistent Kohn-Sham map. So you get some external potential V, which can come from electron-ion interaction as well as the mean field part of the electron-electron interaction. And this Laplacian is the kinetic operator. And you want to solve in some domain a bunch of eigenfunctions. Once you solve these eigenfunctions, which are orthonormal to each other, and you compute the lowest low in the sense that the eigenvalues are the algebraically lowest, lowest NE. NE is the number of electrons. You add them up the square of this wave functions. This is called the electron density. So the learning problem in this particular case would be that you give me the external potential, whether I can learn the electron density rho. Of course, you can be even a little bit more aggressive, which means that I don't start with this effective potential V, but I want to start literally with atomic positions, which are just one group of numbers. And these are the positions of the ions. I want to learn the self-consistent electron density, and this will be the second part of my talk. So we want to use neural network, and in this seminar, I think I don't even need to say that deep neural network has made a big splash. Although this is some old news, but I still find it funny to show that, I mean, which is, yeah, I still have no idea what is the context of this thing. But if you really take this out of the context, I think this is pretty interesting, that AI is more important than fire or electricity. And this is commented by the CEO of Google. I have to say, at least to the extent of my knowledge, a lot of things has happened since fire. So yeah, so we'll see as time goes whether this statement would hold. But nonetheless, there has been a real deep neural network revolution, starting from ImageNet to AlphaGo to recent AlphaFold to recognize the voice, so on and so forth. There are just numerous examples. Kieran very kindly mentioned our Gordon Bell Prize work, and the reason that got us the prize was that we did ab initio simulation, we did MD simulation with ab initio accuracy, which is completely different from ab initio MD simulation. So it's an MD simulation with ab initio accuracy in the sense that the training data are really learned from ab initio MD, but the actual things, a force field propagated by neural networks up to 100 million atoms. Actually, we did a little bit larger than 100 million atoms, occupied the entire Summit supercomputer. At that time, it was the world's #1 public domain supercomputer at Oak Ridge National Lab, until it was taken earlier last year by Fugaku, a Japanese supercomputer. So we compared the time scale and the length scale, compared at least to all the other Gordon Bell or Gordon Bell finalist work. So you can see that on the length scale, because this DFT calculations, it scales cubically with respect to the system size. They are linear scaling algorithms, but there are caveats as well. Generally, they scale cubically with respect to the system size. So although there's a Moore's law and the things are, the computational power is growing quite rapidly, starting from 2006, which was the first Gordon Bell, awarded to Francois Gigi's Q-box code. At that time, it was a couple of hundreds of thousands of CPUs, a couple of hundred teraflops, and did about, if you convert the calculation to an MD time, it will be about 1 picosecond per day. And that was like a couple of thousands of atoms. As the time goes, indeed, there was this, for example, the Japanese Gordon Bell, and that was 3 petaflops with the RSDFT code, and reaching briefly to 100,000, or even this conquest one with linear scaling code with 1 million atoms. But as you really scale the length scale, despite the computer becomes larger and larger, the time to solution actually becomes slower. And so originally you can do about 1 picosecond per day, but later all these things are much less than 1 picosecond per day. So if you use such kind of calculations you want to do, you can do a heroic calculation like for once. But if you want to use this code to do science, that is still a formidable challenge. So with machine learning, that at least gives some hope of going the the length scale to be at least 100 times larger. This, more importantly, the time to solution is at least 1,000 times faster. And so not only we can do 100 million atoms calculation, but also you can do 1 nanosecond per day. So that is, I think really there is a potential to have a very big change in terms of how people conduct ab initio molecular dynamics simulations in the future. Kieran asked me a very good question, whether I did the code. My honest answer would be no. And for this particular thing, because I'm really not an expert in this thing, although I'm giving this talk. So the real leader, as you can see from the list of the orders of the authors, was really Weile Jia, who was my former postdoc here at Berkeley, and he's now a faculty member at the Chinese Academy of Sciences, and also Lingfeng Zhang, who was at the time only a student, PhD student, and at Princeton University, but after graduation, very unusually, he became a faculty. I think now he's at Peking University. And okay, so both of them are excellent speakers. If you want to know more, I would say that, yeah, maybe they can give a talk or something and about more details of what's going on behind. So now, why we're interested, from our perspective, we're interested in deep neural networks in general for scientific computing, because at least for me, I've been very much interested in representing high-dimensional problems for a long time. And as we all know that quantum physics, quantum chemistry, there's just no shortage of high-dimensional problems. Pretty much before, we only have a handful of tools to really deal with high-dimensional problems in general. Yes, of course, there's Monte Carlo, and which is does not suffer from this curse of dimensionality. You can also use some special variational ansatz, which is the bread and butter of quantum chemistry. Also, since there's a tensor network, I don't need to say anything in Irvine here since Steve is here. But the neural network really provides a different way for us to think about high-dimensional problems. So that is the least exciting. It doesn't address all the problems, but it gives you a new angle. So if you look at the deep neural network, it just looks like a bunch of matrix multiplication. In the end, there's a linear layer. But I want to say that most of the working neural networks doesn't look like that. So because these things, if you directly use this for your problem of interest, the performance is usually bad. Locality seems to be a very important thing, as demonstrated by the success of the convolutional neural network and numerous other examples. They're just exploring locality in this or that way. In other words, if you're dealt with a very big image or deal with a bunch of data, you don't directly just say, hey, let's do a DNN, and all the way to spells out a number, but you want to assign some geometry to this data, and then you can say at the beginning, this data, they're aggregated together, and the next level and the next level, in the end, you maybe towards the very end, you assign some sort of this really dense neural networks. And that's really the backbone of many neural network architectures. Now the question is, what about non-local interactions? First of all, I want to give a disclaimer that we don't really say that we have a good solution, definitely not the best solution. We're really not even sure whether we're giving a good solution, but we want to give it a try. There are some obvious ways to handle non-local interaction, which is, for example, just this one. That is, if there's a non-local interaction, I can use this CANs that gradually aggregate information. You can think at the beginning there are pixel levels, and gradually you will get some fingerprints. Let's say it tells you that this number 1 is not only just the pixel, but actually it tells you there's a dog or there's a cat there. So the CAN, in principle, definitely has the capability using this cascade-like structure to learn something about the non-local interaction. But in scientific computing, as far as I know, this kind of a so-called UNet-like structure hasn't really ubiquitously been used, or I don't know how successful they are in practice. And what I'm going to talk about, this multi-scale neural network, is really another way of thinking about it. And I don't know whether this is the best way to think about it. So I'll give you an example. So for example, the Coulomb interaction, this is definitely long range. If you just use one layer CAN, it will fail drastically, guaranteed. So your input are the positions of some atoms called YI, and you want to know, or you can smear it a little bit and use this density representation. What you want is the potential at some point x. So you can sum them up or write as a sort of integral form, or if you want to write in the differential form, whatever way you want. The goal is to learn the U from rho. So this really fits what I said at the beginning. You want to learn this linear map from rho to U. And this is very non-local dependence between U and rho. If you, as I said, the direct CAN won't work. So the question is what works? In terms of the MD simulation, the importance of long-range interaction has also been recognized by a number of papers. For example, I know that the Michele Keriotis group has recently done a number of things along this line, or Alexander Tkachenko and Klaus Müller, and also Kiron is very interested in this. So many people have contributed. So, okay, so there are basically two approaches as far as I know. They don't mix very well. So let me just say what are the two. So which is at the very beginning, you need to decide whether you want to voxelize it, which basically means that whether you want to treat the data as an image, or you want to treat the data as some continuous numbers. And it depends on how you want to do. The neural network structure later looks very different. So our thing falls squarely into the voxelized part, at least for now. So what does voxelize or voxelization mean? So as I said, it's basically you want to map image to another image. So I want to find the mapping from an apple to an orange. This is not how the computer sees it. The computer sees this thing. So you first use some pixels, and what the computer sees is that here the color is a little darker, this is less darker, and blah, blah, blah. And similarly here, this is orange. And therefore, you're really trying to map R, let's call it n squared, Rn squared to another Rn squared. Okay, so these are well-defined discrete numbers, and this n is given. So, or you get from like the apple from a grid, and you want to get the orange on the grid. Okay, so our idea is a direct generalization of a very successful approach in applied math called the H-matrix or hierarchical matrix. It was formalized by Hackbush in 1999. It dates back to tree code and very famous work by Gringard and Rochlin called the fast multiple method. After the H-matrix, there is tons of work along this line, but it's too numerous to list. I'll just list one of them. So the idea is exactly how to efficiently represent a potentially non-local integral equation, linear, which means that your given data is V, and there is an integral kernel called G, and I want to figure out the U. In particular, if V has n data points, if this one is an n by n matrix, this is an n by n matrix multiplied by a vector of size n, the cost will be order n squared. H matrix tells you that if this G satisfies certain properties, then the cost can be reduced to O n log n. So, which is of course a big improvement. So why? It won't work for all G's, but it works for a very large class of G's. The idea is, because this is called a hierarchical matrix, you hierarchically chop your domains into different parts. So you can chop them into very coarse parts, you can chop them into very fine parts, and then you can pretty much think the G's represented as some block matrices.
For example, at the low level, I can think that G, some matrix blocks corresponds to the interaction between this and that, or this and that. So these are the spatial domain. And or at some finer levels, my matrix blocks also get a lot smaller, and each time I will only look at the interaction between this tiny domain and this tiny domain. Is that clear? Okay, so depends on whether they are adjacent or not, and we're gonna say that, okay, so some boxes they are adjacent and some boxes they are far away. So the fact that some boxes are far away is really the most important thing in the idea of the hierarchical matrix. The reason why it is important is because this H matrix has this amazing property. Or you can, another way to think it is that I first define matrices of the following amazing properties to be H matrix, then I try to prove certain matrices are H matrices, the same thing. So the H matrices have the following property that if you look at G corresponding to matrix blocks that are far away, so this 1, 3, it corresponds to an interaction between this guy and let's say this guy, and then that's low rank. So this matrix may be huge, okay? It may be of size 1,000,000 by 1,000,000. That doesn't matter. But for some kernels, maybe this is only of rank 5, let's say, or rank 10, some constant rank. And similarly, for 2 and 4, because they are kind of separated, so this is this is also rank 10, rank 10, rank 10. How do you think about this? It's like I have a bunch of charges that are separated from each other. So if this blob, 2 blobs of charges, they're very, very close to each other, I want to compute their potential, then I really have to figure out where each particle is located, and I compute all of this pointwise interaction. But if they are very far away, if they're really far away, all I'm seeing is kind of like Coulomb's law, and I can treat them as like an effective charge, and they just have a Zi, Zj over Ij, such interaction. I can improve the approximation by including the dipoles and quadruples, and so including more and more multiples. But you can see that no matter how many points are in these blobs each, I don't need that many multiples, and the accuracy should be good enough if they are sufficiently far away. So this is exactly the idea behind the fast multiple method. So Leslie Gringard and Vladimir Rokhlin made this intuitive idea a practical mathematical and algorithmic method for general chart distribution, and Hackbush further formalized the argument and into algebraic construction. So this is basically the history behind such kind of developments. The most important thing is if you consider off-diagonal blocks, then that is low rank. Furthermore, you go to what about these guys? I mean, there are some adjacent guys, and I haven't represented them. When I go to a smaller scale, the size of the box also needs to become smaller, right? So, another statement of the hierarchical matrix is that even though the block size becomes smaller, as long as these boxes are kind of still far away from each other compared to their relative size, then the rank doesn't change, or at least the upper bound of the rank doesn't change. Okay, now you can see that I just go to finer and finer level, and with log n number of steps, I would enumerate everything other than the adjacent blocks at the finest level. But of course, there are order n of them. I add them together, O n log n. So this is the basic idea. So it's a very successful method. And what it means is I have some integral kernel here. It's linear. I decompose this thing into L equal to log n number of levels. Each of them only deals with some low rank matrices. the finest level, we deal with some sparse matrix. So this is a sparse plus low rank decomposition. And furthermore, there's nothing to be learned. Every step is like you can do this semi-analytically if you do FMM, or do SVD if you do numerics method. So there is a well-defined procedure to construct this kind of things. Once you construct it, then every time you apply it, it's going to be O and log n. So
sorry, Lidnan.
Yeah.
So your sort of illustration was one-dimensional, right?
Yeah.
The dimension matter?
Oh, excellent question. So this is the one-dimensional, and for the 2D and 3D, the answer is yes and no. Depends on the kernel. For some good kernels, such as Coulomb, the dimension to some extent doesn't matter. It only says that if the source and the target are kind of far away compared to the size of the source and target, or let's say in particular the source, and then the rank doesn't change. However, in some other things, let's say waves, which is you just in your Poisson's equation, you just add negative shift. Then once it becomes waves, things start to oscillate. So it's no longer that smooth. So you not only need to worry about the size, you also need to worry about the angle, blah, blah, blah. So things get a little bit evolved. And previously was Professor Hongkai Zhao. I believe he's now in Duke, is a leading expert on this topic.
Lynn, a question. So you said this is sort of a deterministic algorithm to find this. Is it iterative?
There are many methods to do it, and but you can definitely make it deterministic. So, for example, I can just literally get this block out, and I compute its low-rank decomposition. The original FMM essentially says that this part, I don't even need to do a numerical SVD. I can even do analytical. Later, you can see that you can also take this matrix block out and do direct SVD. But there also depends on access model. There are other methods.
So do the different levels interact? Do you have to iterate through?
They don't. They actually literally, you can see that this thing, I mean, this part is empty, and this part is empty. All the levels are completely destroyed, at least the normal. But if you want to enforce some discontinuity, you can probably do that as well. But conceptually, this is a completely non-overlapping partition of the domains. Any other question? Okay, so from a linear algebra perspective, and you decompose this matrix into this form. I draw in 1D because 1D is easier. 2D starts to become a little bit messy. You have a bunch of log n number of sum of low rank matrices together with a sparse. And every time we apply the low rank matrices, you can also reshape things a little bit. And so this is often, you can call it like like a restriction operator. There's some middle kernel, and this is something like interpolation operator. Okay, we're actually not that far away from a neural network because, well, let me see. Yeah, so this is just to write down, and every time you first apply this V and apply the middle guy, and you apply this interpolation. And then finally, you have this OM guy, and you just do it with a regular sparse matrix multiplication. If you want to neuralize this, it's really simple because as long as you do a non-overlapping partitioning of your domain, and this interpolation can be pretty easily implemented with the CNN or locally connected network-like structure. And this is just a locally connected or block diagonal matrix with one layer. And usually after your CNN, you want to do some nonlinear operation. But since we're dealing with a linear operator here, there is no nonlinearity. This would be a sparse processing layer, which is linear. Finally, you do a I mixed up the interpolation and restriction. and sorry, so the order was wrong. And finally, you interpolate this back to the original grid level. So all of this can be implemented using a locally connected network. You can do this easily in PRS, setting the width, stride, number of channels correctly, and you can have a neural network or PyTorch implementation of H-matrix, or automatically differentiable implementation of H-matrix. You can definitely do that. So so this just summarizes what I said earlier in terms of the complexity. In terms of putting them together, you just put all the layers together, you get some input, and again, I illustrated here with a 1D. You can copy them into multiple dimensions, give them multiple copies. Each of them go through this restriction processing interpolation. Everything gets something together, and finally add them up, and you have got this neural network representation of H-matrix. There's only one step away to generalize this to the nonlinear maps after written down all the things before, which means that, okay, so this guy, this interpolation, well, so CAN, you can definitely add some nonlinearity. In the middle, because I want to represent a nonlinear map instead of just a linear map, this processing things, while you can still restrict your sparsity, but you might want to add some nonlinear activation functions like a tanh or other things. In the middle, you also want to have a few layers of add a few layers, just rather than just having one layer. And finally, add everything up together, and this is voila, we're done. Very simple, right? So okay, you can further make this a little bit fancier. I won't talk about that. Which is not only there is a H matrix, there is also a version called H2 matrix, which basically says that for all these restriction operators, you shouldn't consider them to be completely independent from each other. There is an underlying hierarchical structure that allows you to reduce nominally the cost from O(n) log n to O(n). This is rigorous in the case of Coulomb, but in the neural network case, I would say things are a little bit murkier. What I'm saying more is that this gives you a different neural network structure, and you can test whether it performs well. Okay, so I show some numerical tests, again, for the voxelized version. And we did this for some non-self-consistent Kohn-Sham map for 1D and 2D, where there are a few parameters. Number of n is the number of the input, dimension of the input, or the number of pixels. L is the number of levels, which is about log 2n, but you can adjust that. There are a number of layers for the intermediate thing, and also the number of channels. So not only just have one interpolation operator, but you can have a few. We measure the error in terms of the loss you can do the L2 or L1 thing. So this is a 1D example. R is the number of channels. You can, and this is the effective potential, which is just a sum of a bunch of Gaussians to see whether it would work. So NE, I forgot, maybe about 10 or something. So if you use, you don't use enough number of channels, you definitely see all this kind of curves, which is really annoying thing if you use the neural network representation, because unlike the smooth functions, these things are not guaranteed to be smooth. So definitely, especially when you don't have enough training data or your network structure is not good enough, you will see all this kind of like non-smooth behaviors. Although if you add more channels, in this case, it will fix that, and the performance looks reasonable. Well, that is the eyeball norm of the accuracy. You can also look at the table, and it gives you a few, digits of accuracy, 3 or 4 digits. Whether this is good enough for electron structure calculations, I don't know, because one thing about neural network representation, well, we can definitely leave this to the discussion session and see, I mean, what's the achievement and the limitations of this as far as we can see. For example, if you ask me to go to 10 to the minus 5, I would just say I couldn't do it. And that's, you can reach some level of accuracy. Some bad network structures won't get you here. You may be stopped at 10 to the minus 1. But if you really want me to go to 10 to the minus 5 or 10 to the minus 6, I would say I just cannot do it. So you can also compare with the CNN-like structure. We tried to be as fair as possible, but there are just too many parameters to tune. So for CNN, you can use similar number of parameters compared to the multi-layer neural network. The error is also a bit okay, although MNN seems to be a little bit better here. Does this mean that the multi-layer neural network must outperform CNN? I don't know. But for this example, this is the best, the fairest example we can compare. So at least it says that the MNN is not a disaster. So for 2D, you can do similar things. Again, I can go to 10 to the minus 3, 10 to the minus 4. If you ask me how to go to 10 to the minus 5, I can't. Okay, so this is the first part of the talk. Let me see the time. Okay, I have a minute or something. So any question? Okay, so if not, I'll continue. The second part is to throw everything I've developed away and talk about the meshless algorithm. And here I have to just acknowledge that, admit that our first thing was to try this MNN on real system for 3D, and we failed. So that's why we go to a different route and go to the meshless, which is the not voxelized approach. The goal is not to just deal with model problems. We want to deal with the real chemical system. And it's basically this so-called deep density is an extension of the aforementioned deep MD structure, the Cornwell thing. And here, how should I say, there's only short range mapping. And I'm going to talk about long range thing at the end of the talk. But in this architecture, there's only short range thing. You might say, well, you just talk for the whole talk, the importance of the long range. Yeah, that's for the discussion. It's a not so clear cut whether this thing is important or how important they are. So the mesh-free approach, there is some limitation. Remember that the MNN is basically mapping a field to a field. So I have a potential field, Vx, and I get a density field, which is rho x. Okay, so in order to get a mapping from field to field, the only way I know is to voxelize it. But in some cases, for example, in the case of learning the self-consistent electron density from the atomic positions, we don't necessarily need to learn from a field to field. We actually want to learn from a bunch of numbers to a field, which is quite different. Because although this thing can be viewed as an image, I also have the choice not to view that as an image, okay? Which means that in order to get the mapping rho, the density, at any point, x for the electronic degrees of freedom, at this like ionic positions, I can secretly throw x to the left-hand side and try to learn this aggregate mapping rho xr. Previously, it was like you don't have this x on the right-hand side, you just learn the entire rho x, okay? But this mesh-free thing is you put this x as a variable, and then you learn this rho xr. So the disadvantage is that this won't work for all the fields. It only works with the fields that you know how to parameterize. The advantage is that you can forget about the voxelization, and for example, next time you have a final grid, or if you have a point that is off the grid, then there's no problem at all. And I can at least predict. How accurate, I don't know, but at least I can predict. So this is the mesh-free approach. Why we do meshless? Well, the most direct reason is we didn't make the mesh full method work, but you can definitely argue a few reasons in hindsight, which is, for example, if you do the mesh full thing in 3D, the training is just very, very hard. Even if you give me a few snapshots, that's like millions of degrees of freedom per snapshot. It's a huge amount of memory. Whether we want to parallelize, we didn't decide. We weren't very much, we didn't decide we want to go down that road. And also this meshless approach is a lot easier if you want to enforce some physical symmetries, not just like a D4 symmetry, that's easy. But if you want to have some rotational invariance or permutation equivariance, so the meshless things is a lot easier. And there's also higher amount of transferability, because if you start with some local network, you ask me to train it on 32 atoms and predict the density on 128 atoms, it just becomes a lot easier. Or if you want to go from coarse grid to fine grid or fine grid to coarse grid, so these things, they are all much easier with a meshless approach than the meshful approach. So
then about 10 minutes more of presentation.
Sure. Okay, so I think I said that. And there are a lot of recent works. I think I'm a little bit out of date on this topic for this particular problem. So you want to start from the atomic positions and you want to get the density. I believe these two works were the pioneering works done by Kiron and collaborators using kernel methods. And these two should be from Karyati's group. They refined this with some Gaussian potential methods. There are also neural network approaches. This one, I believe, is a voxelized approach, and these two are meshless approaches, but there is some difference in terms of the architecture from ours. And also, we believe our result is slightly better. So, okay, so since I'm running out of time, let me see. So I'll just talk briefly the structure, the idea. So the idea is that let's look at the one-dimensional problem. And in this case, there's really not that much difference between 1D and 3D, believe me. So 1D makes it easier to draw pictures. So this triangle is an electronic position. I want to know the electron density at this point. And so these circles are the atomic positions. So we want to learn this mapping, okay, this row. And the basic idea, forget about the formula. The basic idea is very, very simple. So I look around, which is for this electrons around, for each atom I look around this neighbor. I try to figure out the contribution of this group of atoms to this electron. So this is what we call like an atom-centered approach. There's also an equivalent, not so equivalent, alternative viewpoint, which is electronic-based approach, which is I fix the electrons, I only let the electrons look at its neighbors. So there are different people do different ways. We do this atom-centered thing, has certain advantages, also certain disadvantages. And then your problem becomes much more local, and you construct a sum network, and finally add everything together. So this is a non-unique partitioning of the electron density, but nonetheless, you rely on neural network to learn it, and hopefully the resulting would be transferable, and then that's it. So there are, okay, so this is the locality part. So you want the neural network to satisfy a bunch of symmetry properties. The most important thing we found are permutation symmetry. So if you have two hydrogen atoms in the neighborhood, I permute the index, it shouldn't matter, and rotational symmetry. So global rotational symmetry shouldn't matter. This is how the neural network structure looks like. Let me just say very briefly that starting from the input, the electronic degrees of freedom, and the neighbor aggregated atomic positions, you get some descriptors locally, and then from the descriptor, you pass through a ResNet and get a number. That's a local contribution to the electron density from this group of atoms I, and you add them together. So there are some other details. I'm not sure people would care very much. So let me just show some results. These are the 1D, which works much better than I thought. So we tested for 1D insulating systems that you can see that there's a gap, metal, which is basically a homogeneous, close to be something that's like a homogeneous electron gas, because you can see the density varies from 0.195 to 0.210. So it's a very, very metallic. And or I have this artificial metal insulator interface. So it's basically half of the metals and half of the insulator, you put them together and tune the parameters so that the SAF converges. This one does have SAF. So we want to learn the mapping from the electron density, the position to the self-consistent electron density. And what is actually interesting is that if you want to learn the non-self-consistent one, the result is terrible. You just cannot learn that at all. But in the case of learning self-consistent electron density, for metallic system, the screening effect due to the self-consistency becomes your friend. It's an actually incredibly powerful friend that you just take a very small number of neighboring atoms. This is what you get. I mean, even like 2 neighboring atoms or something, the result is incredibly good. In 3D, especially for water and aluminum, especially for aluminum, we didn't see such superb screening effect. This is something we don't quite understand. But this quite surprised me that even for this system, which is really it was a pain in the ass to really just to converge this, because there's a lot of charge sloshing and other things. And the machine learned density was really, really good, at least by the eyeball number. So we also did this for small molecules, from CH4 to some other isobutane to the butane. So you can learn the electron density. You can measure this. I believe this should be a fair comparison compared to what, for example, Teriotti and collaborators reported. I think our results are slightly better. And you can also measure other things like dipole, glucose. They're, again, reasonably accurate. So if you want me to further, this is already pretty good. So less than 1%, much less than 1%. But if you really want me to get to 0.01%, I just have absolutely no way to get it. So we also tested larger problems like water. We also tested the transferability. You go from 32 atoms to 256. I think we also did 512. So this is, to our knowledge, the largest learning density problem that is presented in the literature by the time we submitted the paper. I don't know whether there are recent things, because if you really go into the code and you do the inference problem, it's really bad, because you just have a huge snapshot, like 1 million points to infer, and each of them require a bunch of calculations. It's really expensive. So, but nonetheless, you start from a small problems to train your network, at least by eyeball norm looks okay. And you transfer to 64 atoms, still okay. If you look at the error, that's about 1 or 2% of the error. Whether that's good enough, again, I don't know. And you can go to larger, it still looks okay. And the error didn't really dramatically become bad. And you can also look at the error of the density plotted in this way. And for small molecules, just superb. And for this is like a point-wise value, and that's why the energy becomes smaller. The difference becomes like a smaller here. You have a bunch of things. And also for the water, it's not that bad either. Okay, let me conclude. So in terms of learning this seemingly, I think seemingly non-local mapping, non-local nonlinear mappings, there are at least 2 ways you can think. One is to voxelize, the other is to do the mesh free. There are advantages and disadvantages. We still haven't figured out which is the way to go. But more importantly, this mesh free approach so far is very much like local network structure. It's kind of amazing that it already, if you use a very loose term, renormalizes some of the long-range effect into the short-range model. But of course, it is very hand-waving and is doomed to fail if you create some very heterogeneous problems, and just by definition won't work. But what is the best way to deal with long range and mesh free? We don't know. And we did some initial work along this line, generalizing the so-called, or neuralizing the so-called non-uniform FFT. And finally, thank you very much for your attention.
Oh, thank you. Maybe we can stop sharing the screen for at least a minute to see. Okay. So does anyone have questions for Lynn? If not, I can start. So this this H matrices idea, right? If I sort of, you represent it as this integral equation, but if I'm using a basis of some kind, like a localized basis or something, is it still possible to do this?
The short answer is I think it works. So it doesn't depend that much on the details of the basis. It depends more on the overall smoothness of the kernel. So if a Coulomb that is pretty smooth, even though you use some locally smooth but functionally like looking functions, I don't think it matters. Coding wise, things becomes a little bit trickier, but I don't think conceptually
it shouldn't make any difference, right?
Yeah, I believe that in the field of quantum chemistry, some people like Edmund Cho and collaborators have already been using similar ideas to at least asymptotically accelerate the calculation of the electron repulsion intervals. Whether it is prime time in practice, I'm sure asymptotic is good. Whether it's prime time in practice, I don't know.
Yes, there's an awful lot of tricks and things that people have to.
Exactly.
Okay.
I have a question. Hi, Lynn. Very nice talk. You mentioned the matrix decomposition. So that's the linear part for a neural network. How's the? Could you say something about the nonlinear part in the physical problem and how the approximation managed to take care of that part? Yeah.
Okay. Yeah. Very good question. I didn't say very much because there's not much to say, other than saying that we tinkered a bit. And insert a few layers there, tested a few activation functions. Some of them didn't work, we discard. And so
okay.
Yeah.
Mm-hmm.
Yeah.
All right.
There's really not that much like intelligent things to say.
Okay.
Lynn, I think in some of your other work, there are little proofs and things. But I get the feeling there aren't so many proofs in this case, especially when it's nonlinear.
For this one, yeah. I mean, there are some theories like on this, and I tried to follow a little bit, and quickly realized that the field is moving way too fast, and I'm not even close to the frontier. So I completely give up, like in terms of contributing anything theoretically to this field.
But did I see that Wayne Ann is proving theorems about?
Oh yeah. He made quite a number of contributions recently, and some very interesting works like Baron spaces, and I follow the papers, but I have zero contribution.
Okay. Do we have more?
Yeah, I have a question. I'm not sure how to formulate this, but in the hierarchical approach, as you make the little boxes, it seems like you have a little bit of sharp edges, edges of the boxes, which, you can think about ways of trying, you can try to figure out whether that causes any, loss of accuracy or efficiency. And, part of the ideas that are sort of part of the mirror tensor network, which are in common with wavelets, are to sort of smooth out the edges. I'm trying to understand if there's any sort of advantage in this sort of approach to anything that sort of pays attention to trying to use, you know, sort of partial diagonalization in sort of energy space to sort of decompose things both in space and energy at the same time, or momentum.
Okay, yeah, so if I understand your question correctly, you're mainly worrying about the non-overlapping, strictly non-overlapping partitioning of the domain.
Right.
Which is of course very legitimate. And so I would say that on the positive side, you can think that this is integral operator. You have already discretized that, and you end up with a algebraic problem. And for each of the matrix blocks, your SVD, the error of the SVD can be controlled. So you can literally control the errors for each of the parts, and in the end, you can control the total error. So it's a very legitimate approach. It's not like you're getting something dramatically bad.
Right.
But if you don't do the SVDs very, very accurately, of course, weirder things could happen in the middle. And in that case, what Kieran suggested earlier, which is to use a basis and then do, because it's less of a crime once you formulate an algebraic problem while the underlying bases are nicely looking, right? So because you're then doing a linear combination with smooth basis. So that would be one way to do it. You also mentioned the wavelets, which is of course a very interesting direction. I think something has been done along this line. So my collaborator, Lexing In at the Stanford in the past 2-3 years have made a number of contributions to the marrying the fast algorithms with the neural networks. I believe that he did some butterfly-based things, wavelet-based things, different flavors of wavelets, and tried them with the different neural network structures for inverse problems. Maybe you can check out like his work, or maybe get him to talk about something here. And yeah, so something has been tried along the line, but I'm not an expert.
Mm-hmm.
Do we have any more questions? As usual, I sort of butchered my introduction. I forgot to mention that Lynn is either PI or co-PI on about half a dozen grants as well, and is currently producing about a dozen papers per year. Now, I think most of you know that my definition, one of a key attribute of a true mathematician is that they never do anything useful. And so by my criteria, I'm afraid I have to declare that our visitor is no longer really a proper mathematician. Because
I never considered myself to be one.
What's that?
I never considered myself to be one. It's a quite honor for you to call me, not to call me as a mathematician.
I think we share a certain sense of humor. Yeah.
Yeah, my colleagues, yeah, don't, send this, put this in your recommendation letter about me to my colleagues. So that might do some damage, but otherwise I'm honored.
Okay. So, well, thank you very much. This was very nice. So let's thank Lynn again.
Thank you.
Thank you.
And we'll have another seminar in about 3 weeks from a young chemist in Stanford. Okay. And again, if anybody has people they would like in the series, please let me know, especially from Earth System Science. Okay.
Okay.
All right.
Bye.
Thank you all. Have a nice set.
Yeah.
Thank you.
And we'll meet on my.
Okay, I'll log out then.
Okay.
Thank you.